Okay, so we're going to look at this reading on Introduction to Linear Regression. And, I want you just to keep in mind that there's only a couple of questions coming. Don't get blown away by this material. I think that they're going to be very close to the examples that you see in the curriculum and go through questions from the online learning system from CFA Institute to familiarize yourself with what you're looking at. I think that's critical. You really need to know what you're looking at to be able to answer these questions. That's how I think you're going to be able to tackle them in just the minute and a half. Okay. I also think this is given to you as a way to smooth the transition to the next level where you're going to jump in more detail. Okay, so with that, let's jump right in here. And our learning outcome statement wants us to describe simple linear regression model and the roles of the dependent and independent variables in that model. So just to take a step back here, what we're looking at is trying to look at data and say, is there a relationship between two variables? So let's just expand this screen and we will write on the side over here to be able to give us a little bit of background. So we're looking at two variables, and they're labeled as X and Y. And the X variable is referred to as our independent variable, and the Y variable is the dependent variable. And what it means is it relies on X. There's some sort of relationship that that X has an effect on Y. So it could be something, like you're an analyst and you're looking back and you're trying to see, okay, well, let's look at the GDP for a country, and let's try to draw a relationship between GDP and we'll put in something here, something like consumer spending. Okay, consumer spending. So which would be dependent upon the other? Okay, so we could argue that GDP is derived from, among other factors, consumer spending. So what I want you just to take away from this is that the GDP would be the dependent variable, DEP, and the consumer spending then would be the independent variable. So there it is. We've got this cause and effect. So there might be a change in consumer spending that affects GDP. That would be our hypothesis. And through regression, we're going to come up with a simple mathematical model to be able to identify this. And our model is over here. And so just to expand upon this, it just simply looks at the independent variable. And this is nothing more than a simple linear relationship, a straight line. You may remember this from your high school days in math, where you had y is equal to mx plus B. You may remember that, where M was the slope and B is the intercept. And so from this, we can now translate this over to our regression. So what we can start to look at here is a simple model. And now instead of just writing it as we did back in those high school or university days, well, let's just draw a little picture to see what we're looking at. We've got these two variables, and on a diagram here, we've got the independent variable X, and we've got the dependent variable Y, whatever it is. And we're looking at a number of observations. We're looking at, we go back and we start looking at these observations, and these are, might be historical values and such for, could have been back to my example of consumer spending and GDP. And through this, this process of ordinary least squares, okay, we will come up with a line of best fit. That's what we're after here, this line of best fit. So, so we will come up with some sort of regression line. And this regression line then is a linear, it's a straight line that allows it to be, quite simple in terms of the mathematics. And now it allows us to be able to understand relationships between the independent and dependent variable. We can start to make predictions and such. So this is really where we're headed in terms of the of this material. And so we've got to be able to derive this equation. And as we've written, the equation, I tried to go back to this simple, high school university formula, but let's just use ours. So we have y is equal to, I've got the intercept, which is beta naught, plus the slope, which is beta 1, times my independent variable, whatever that value is. And then there's going to be some error term, plus e. And this error term relates directly to our diagram. So as you can see, these dots are not exactly on the line. There's differences between the dots and the line of best fit. And that represents the error. So the error in terms of the difference between the actual values and the predicted values by this line, this is captured in our standard error of the estimate. And so we like to look at these models, and we want models that are useful. So we want models that have low standard errors. Okay, that means that these observations are really close around this line of best fit. So some key concepts that you need to take away right away without getting blown away here, okay, in terms of being able to describe a simple linear regression model and the roles of the dependent and independent variables. Okay, what we're doing is we're just looking at different variables. They could be macroeconomic variables, consumption and GDP. We're trying to derive a relationship between these. We're looking at the actual past data, and we're trying to draw this line of best fit. It's linear, it's a straight line. That's it. And so now we're going to analyze this, and we're going to use it to say, how useful is this model? How useful is it in terms of its predictive power? And can we rely on it? Remember, we're investment analysts, and we're using this regression to come up with our inputs for our models. And just to digress, you may remember this type of formula. For example, the intrinsic value of a security is equal to, well, let's talk about the dividend next year, D1 over R minus G. So that's the value today. So we might use regression to be able to estimate the growth rate. And we might use, company sales, and we might use other factors, or we might use regression to figure out and estimate our discounting rates. So we're using regression in terms of as an input for our valuation models. That's really what we're doing. So you're not a statistician here. Don't get too carried away. Okay, this is really where it drops into our process of being the equity analyst. So we've got to then understand the language. I want you to know about this language, the line of best fit. Okay, we understand that. Here it is, the line of best fit. The standard error of the estimate. Okay, well, that's this error term here. So that's relating to how far off are the actual values from what's predicted by this line. Okay, so that's really what I want you to take away, and I want you to be aware of at this point. Okay. Now, as I'm saying in this comment here, you only have a minute and a half to do each question. There's a lot of scary looking formulas in there, and some of them reach back to other formulas that we may already know. You might recall them from your earlier readings in the quants. And so I've listed a couple here. These are, calculating covariance. I want to bring that back, calculating standard deviation, and calculating the correlation. And, the reason why I wanted to throw these in here is there's a linkage. And so, from the statistics, these formulas that we may know from the other areas of this curriculum, well, let's come over to our regression. And in terms of regression, our regression, okay, well, let's try to match this up. Well, remember, we're talking about an equation, and we're talking about an equation y is equal to beta naught, the intercept, beta 1, the slope, and an independent variable. I'm going to forget about the x value, the e value, the error term. We can drop that off. And the first task that you may be asked in terms of a question is simply estimating these parameters, estimating these coefficients. These are referred to as beta coefficients. And you may know that from the hypothesis testing material that you've gone through. So what I want you to be aware of is to try to draw a parallel from these formulas that you know to be able to figure out these formulas. So how do we figure out the slope coefficient? Well, the slope coefficient, it's going to be really close to, and you can draw a link here, to figure out this slope coefficient, draw a link right back to this correlation. Okay, so why do I want you to draw a link back to that correlation? Well, here it is exactly, because if you wanted to calculate and estimate this slope coefficient, you want to estimate that slope coefficient. It is the covariance of x and y divided by the variance of x. So that's going to look something like this. So that's going to be the covariance of x and y over the variance of x. And remember, variance is equal to the standard deviation squared. So, okay, it's not exactly this formula, but it kind of looks like it. And let's expand that further. What's the covariance of x and y? Okay, well, here's the covariance up here. And we've got actual minus expected. Actual minus expected. That's the only way I could type it. Okay, so we'll use bars and things. So the actual value of x minus the expected value of x bar, and the actual value of y minus the expected value of y. And this is divided by the variance of x. So what's the variance of x? Well, okay, the variance of x, that's related to our standard deviation formula, variance and standard deviation. So remember that standard deviation SD is just simply equal to the square root of variance. Okay, or you may just remember that, here it is, variance, we'll write it right here, variance, VAR, is equal to the standard deviation squared. So okay, so if we square, and let's now just get rid of some of these lines so we can see it here. Okay, if we square this value, what does it do? It just removes the square root sign. Okay, so what we're left with in our formula is just simply the sum of the actual minus the expected value squared. Okay, and you now are looking at your formula for being able to calculate this slope coefficient. And I think that you've got to, be aware of this, okay? And, I think they could give you a table. I don't think that you're going to, actually have to derive the table. I don't think you're going to have time, but, you never know with CFA Institute, okay? So I wanted to make sure that you could draw these parallels. That's how I remember these types of things. So I think that's how you can remember them too. Now, a few, sharp people out there might just be saying, okay, well, hey, what happened to this part of the formula, n minus 1 and n minus 1? Well, through the mathematical gymnastics, those are canceled out. I mean, take a look. If we divide this covariance and we divide it by the standard deviation squared there, you can see, if I can divide this, you'll see that the n minus 1 cancels out. Okay, if you can't, then don't worry about it. Okay, trust me, that's what you got to go with here. Okay, and so I think that you've got to be able to handle this formula to be able to calculate beta 1, the slope. And so what I want you to take away here is I want you to know that it could be given to you in a table format. That's why I said you've got to know, how to interpret the information and the values of what you're given. Okay, so they could simply say the covariance of X and Y, they give that figure, and the variance of X, okay, that's our signal for calculating slope. And then they could also drop you right back to the actual minus expected values, over the squared deviations, the variance of X, of the independent variable. So be ready for these. There's an example in the curriculum that goes through. I think those shaded box examples are really what you want to make sure that you go through. Okay, so this is the first one, estimating the slope coefficient. And now if we turn our attention from the slope coefficient to the intercept. So if we want to now estimate this intercept, well, okay, this is really just going to be backed out here. And so the intercept, is just going to be beta naught is equal to, well, we'll have a value of Y minus beta 1 times X. So that's it. It's just backed out. So you're going to have to calculate beta 1 first. And then calculate your beta naught, your intercept. So I think that these are the parameters that we need. And once we have beta 1 and beta naught, then what does this allow us to do? Okay, let's put it right back up here. It allows us then to come up with this line of best fit. Okay, so keep this diagram in mind here. As we put it in, we have the X value and we have the Y value. And then those actual values, the observed values. And now what do we end up? We end up creating this line of best fit. And there it is. Here's my line of best fit. And this is now described, this line, this equation is now described through the equation Y is equal to beta naught, that's the intercept. Okay, remember, don't lose your mind, there's the intercept right there. And then the slope coefficient plus beta 1 times X. And this slope coefficient can be negative, okay? So I don't want you to just think they're always positive, but I wanted you to be aware of this, okay? And I wanted you to draw the parallel back to material that you've seen before. And then I just gave a quick learning example here. And really what I was just trying to do was trying to give you, material that you're like, oh, what is all this? Okay. Well, okay, don't lose your mind. Okay. Really, this is nothing more than the actual minus the expected. Actual minus expected. That's how I had to type it. Sometimes, you may see it that way. And, you can match these right back up to the formulas. Okay. And so how could we calculate this, this standard sample standard deviation for ATC? So I've got stock ATC up here and I know exactly, okay, I just wanted to make sure that I remember the formula for the standard deviation. It's the square root. Okay, so just remember to calculate the standard deviation. It's the square root of the sum of the squared deviations. So that's actual minus expected squared over n minus 1. Okay, so just remember we've got this in terms of the standard deviation. Okay, so what do we end up doing? We end up just plugging this information in. I can grab this information. They already gave it to me right here at the top. Okay, so the sum of the squared deviations, it's right here. It's 391. So this is just 391.5 divided by n. Okay, well, okay, I skipped that from the question. It said that there were 92 observations, if I remember, 92 days worth of data. Okay, so we can drop that in here. That's 92. And remember, we've got to subtract 1 because this is for the sample. Okay, sample. Take the square root of all this, and we'll come up with the standard deviation, which I think is 2.07. Okay, so I mean, that's the closest to choice A here. All right, so listen, I just wanted you to be able to work through this. Like I said, practice this type of calculation, getting used to looking at these scary looking formulas. That's all I wanted you to see here. And I think that that's going to help you in terms of building your confidence to be able to tackle these questions that are going to be coming that are related to our linear regression. Okay, so let's press on here now to the next learning outcome statement. So they want us to describe the least squared criterion. Okay, least squared, I mean, this is, ordinary least squared regression. It's really just a simple form of, mathematical relationships. That's all. That's why it's called, ordinary. Okay, but I really think that you've got to be able to then take this right down to, as it says, to estimating the regression coefficients and their interpretations. So the intercept and the slope. Okay, we've got those. Now, dropping to the next learning outcome statement, they want us to explain the assumptions underlying the linear regression model and how the residuals and residual plots indicate if these assumptions may have been violated. So, okay, really briefly, I put this down here about what are the assumptions of linear regression. The first one is that there is a linear relationship between the independent and dependent values. Okay, there's a straight line. Okay, later on, we'll see other models. And, when you get to the next level, you'll start to talk about other models which are not linear. Okay, but if this is violated, then the relationship, the model is compromised. It's not useful. So any predicted values, based on it will not be helpful. Remember, we were thinking about an analyst trying to predict growth rates, trying to predict discount rates. Well, you use that in your valuation. If your model's garbage and there's no relationship, then it's not useful. So we can look at this plot. So if I get rid of the line, I look at these dots here. Yep, that plot, that kind of gives us this indication that there is some sort of relationship, a linear relationship. Doesn't have to be upward sloping. I just chose that here. Okay, so this is how we are looking at the residual plots. I mean, if I look at these residuals, they're pretty close. The difference between the actual values, remember, the residuals are the difference between the actual values and what's predicted by this line here. And we like to see just a nice uniform pattern. And so, I'm just going to draw this kind of line here, something like this, like boundaries. So let's put these boundaries in here. And so what this shows is that these residuals, that these actual values, they're pretty well constant. Okay, there's no pattern of it going off in different types of directions, like fanning out, becoming wider, or coming back narrower, or something, fanning out. So this leads us into the next assumption of homoskedasticity. So it means the residuals don't form any waves or patterns around the regression line. It's nice and uniform. Okay, if there was this patterns, then that's referred to as heteroskedasticity. And if the model's heteroskedastic, then there's going to be compromises to our analysis. We're going to start to overestimate whether or not these regression coefficients are statistically significant. So keep that in mind when you start to think about this. That again is waiting for you at the next level here. Okay, heteroskedasticity. Okay, and really what the issue here is just thinking about. We're going to think about testing. We're going to test or we're going to run hypothesis about beta 1 and beta naught and beta 1, to see whether or not they are statistically significant or different than 0. And if there's heteroskedasticity in our model, then these tests won't be reliable. Okay. Independence. Okay. Well, we assume again that the observations and that the residuals of those observations are not related. And what we mean by this is well, let's get rid of these lines. Well, when we look at an observation, and let's put this in here. So I'll put a big dot in here. Okay, so here's an observation. And I look at the next observation, and is it something that's below the line? And then I look at the next observation, and is that something that's above this line of best fit? If I see this kind of pattern, then it means that the residuals are not independent. There's some sort of statistical dependency. There's some sort of relationship. Okay, and again, the implications are that our coefficients, our tests for our coefficients won't be reliable, and our model predictions and the predictive value will be compromised. So we think about things in terms of serial correlation, whether it's like negative serial correlation, or if you see something like this. Okay, I mean, I really doubt that you're going to be going back to these kinds of plots, but if I put this in here, a lot of observations above the line, and then all of a sudden you persistently drop below the line. Okay, so this may indicate that there's again there isn't an independence of these residuals of the observations, and there's some sort of autocorrelation of those residuals. Okay, I don't want to overload you with the technical terms. Okay, I don't want you to get blown away there. What it just simply means, again, think about it as when we run these tests on these coefficients, that's compromised. So the explanatory power and the usefulness of our model is compromised. And the last assumption is normal distribution of the residuals. Okay, I'm just going to say that makes the math easier, where there's no skewness to be to come into play. We can use the central limit theorem and then be able to use this in terms of making predictions and confidence intervals. So it makes the math a lot easier for our drawing conclusions. Okay, so I think that you should know these assumptions. Okay, just make sure that you know the basics there, and you can map it over to the picture here of what I was trying to draw, and that really answers the second part of the learning outcome statement, which I think a lot of people tend to ignore, even at the next level where they have the very similar learning outcome statement. So keep that in mind. They could very easily give you this kind of plot or graph, and you might have to interpret that. I mean, that'd be pretty difficult. Okay. All right. So now let's clear some of this off. I'm going to keep this picture up here. And now what we're going to do is we're going to look at this model which we've created, and let's check off the assumptions. Let's say those are there. Okay. So now, how do we know how reliable this model is? Well, we can start to look at different parameters, and the first parameter is the R squared, and that is the coefficient of determination, and this tells us how well the line fits the data. Okay, so a higher R squared is preferable. That means I've got a higher explanatory power. There's a stronger relationship between this dependent variable and the independent variable. And now I want you to make sure that you know this definition. Okay, this is something that you've got to make sure that you're comfortable with. Okay, so R squared tells us the variation of the dependent variable that's explained by the variation in the independent variable. Okay, what the heck does that mean? Okay, don't dive too deep. The variation in the dependent variable that's explained by the variation in the independent variable. If that shows up as an answer question, send me an email. Okay, just say thanks. I'll know what you mean. Hey, don't tell me the question. That could violate the charter. But come on, what else are they asking? This is gotta be there, in my opinion. So I think you've got to be ready for this. So it definitely tells us how well the line fits the data. That's it. So you know, an R squared of 0.9 says 90% of the variation is explained. Okay, so you've got to know this, and you've got to know how to calculate this. And so we're going to calculate this, and you know, whether we have to go back to, you know, basic formulas, okay, or one step at a time is really what I think we've got to do here. So we take this model apart, and let's put this model together here. And this is going to lead us into, you know, some of the components where they start talking about, you know, ANOVA, and you know the learning outcome statement here about calculating and interpreting the coefficient of determination, okay, which we've interpreted it, okay, we're going to calculate it. I'm going to show you how to calculate it in more detail, and then calculating the F statistic, okay, and I'm just going to put up on the side here so that we can remind ourselves here. So remember, I was mentioning that we want to test the intercept, and we want to test the slope coefficients. So in order to test the statistical significance of these, so that should say test, in order to test the statistical significance of these, we're going to do an F test. And as a matter of fact, we're also going to do a T test. Okay, so I'm going to show you both of them right there. So we will go through that F test as well. And as long as we're on the subject of testing, we can even run tests of correlation. We can look at the independent variable and the dependent variable, and we can run a test of correlation. So I'll just write CORR, correlation. And again, that's going to be a type of a T test that we're going to run. So in this learning outcome statement of the calculating and interpreting the coefficient of determination, the R squared, the explanatory power, we've got that. Okay, that's easy. And we now know what that means. I'll show you how to calculate it. We'll break this down a little further. The F statistic is going to be used to test the coefficients of the model and to test whether they are statistically significant. And as a matter of fact, here in this simple single linear regression where we only have one independent variable, there's really no difference between the F test and T test. Okay, they give us the same results. Okay, when you get to the next level and you start talking about multiple regression where there's more than one independent variable, that's where this will start to change. So I think that we need to be able to then go back and now talk just in general terms about this model again. And now that we have an understanding of, you know, how we're analyzing this model, so what we need to look at is we're talking about variation. Okay, you know, how far does it deviate? You know, how far did it deviate from the predicted value, which is the straight line here, and the actual values, okay, or average values. So I can look at this regression model. Here's my regression model, and I can find the variation in this model. The variation in the model is known as the SSR, the sum of the squares in the regression model. And it's calculated as the sum of the difference between the predicted values of y, so you might see this as y hat, minus the average value of y. Okay, and this is squared because it's the sum of the squared differences between the predicted value. That's a little hat, by the way. Okay, I want to make sure that this gets drawn in there correctly so we can see this. This is a hat. Okay, and the predicted values, that comes from the regression line. okay? And the average, well, you would just simply be given the data and you would just calculate the average based upon the Y values, okay? I believe that would be given in terms of a table. You can see some of the examples. Now, remember the error terms here, okay? Remember that error term, you know, kind of circulating all around this difference between actuals and the predicted values there. And so now the error terms, we need to look at the variation here, the sum of the squared in the error terms. And so this is just the sum of, and now we have the actual Y observation and the average Y bar squared. Okay, so the sum of the squared of the error term. Okay, remember the error difference between the actual and the predicted value there. So okay, keeping this in mind here. So the SSE, it's calculated as the sum of the squared difference between the actual value and the average for Y. Where are you going to get this average? They're going to give you a table and they're going to give you the X and Y values. Come on, they've got you. And then you can just simply add up the Y values and divide by the number of observations and you get the average. When we add these together, we get the total variation in the model. So we get the SST, the total variation in the model. Oh, you know something? I think I blew it here. Sorry. Let me just back up. Okay. That SSE, okay, and I'm drawing it right here and I couldn't get my eye on it. The difference between these actual values and this regression line, that's a predicted value. So I completely blew it. It should not be the average. Okay. It's gotta be the, let's put this back here. It's gotta be the predicted value. So let's make sure that we can do this and we're not running into any problems here. Okay. So we'll put that back in here. This has got to be a Y with a hat. Okay, so SSE, this sum of the squared of the error, that is the actual value, these dots here, minus the predicted value by this line. Okay, I've even drew it there. It's the squared deviation. Okay, we've got it. All right, I hope I recovered from that. Now, the total variation in the model, okay, the SST, this is now the difference between, okay, this is now calculated as the sum of, so this is the sum of the actual Y value minus the average Y value squared. Okay, I've got my formula straight here. Okay, I hope that I didn't throw you off too much. So I want you to be familiar with this language, okay? Sum of the squared, okay? Sum of the squared in the regression model, the difference between the predicted value and the average squared. The sum of the squared of the error term, sometimes that's called the residual. That's the actual value minus the predicted value. The difference is squared. And the sum of the total, sum of the squared total, the total variation in the model, that's the actual value minus the average value squared. And you're going to get these in a table. That's where I think that it's coming. Okay, that's what I think. They have to give you this. Okay, so now knowing this information, I think they're just going to give it to you. How do we calculate this coefficient of determination? Okay, it's the explained variation, the variation in the model, divided by the total variation, SSR over SST. There it is. So that's what I keep in mind. That's what I'd look for. On your exam, you know, if they walk you back to a table, that's a little more difficult than, you know, if they just give you the SSR and SST. The other point that you could take away is they could give you the correlation. They could tell you the correlation between the independent and dependent variable. and that correlation squared is equal to the coefficient of determination. So two quick ways to be able to calculate that coefficient of determination. Okay, we'll see how to calculate that F stat, okay, which we will get to. Okay, and so in terms of calculating our F stat, okay, let's drop down here and fill this in. Okay, so we want to determine if the model's useful. We want to determine now, let's say if one of these coefficients, it doesn't have to be the intercept, it doesn't have to be the slope, any of them. If we want to determine if they're statistically significant, statistically different than 0 is what we're really saying. So we're going to use the F stat. And to calculate this F stat, it's the MSR over the MSE. So where are we getting this from? This is going to take us into the ANOVA table, which is the next learning outcome statement, which says describe the use of analysis of variance, which is ANOVA, in regression analysis, interpret an ANOVA results, and interpret the standard error of estimate. So we'll calculate that standard error of estimate, but we're also going to calculate from that ANOVA table the F stat and the R squared, because the ANOVA table is going to contain this information, and I'm going to show you that. So I just wanted to write it out here. Don't get bent out of shape yet for this F test. Okay, how do we make a decision? You're going to calculate your F, and then you're going to compare that versus some sort of critical value or rejection value. And here's your decisions. If the calculated F stat is greater than the critical value, then you reject your null. And the null might be something like the beta is equal to 0, the beta is not statistically significant, something like this. Remember, we're always testing the null. The alternative is what we want. We want this. We want to see if this is statistically significant. We want to see if beta is not equal to 0. Okay, it's equal to some other value. Okay, that's really what we're testing. Reject this null hypothesis. Okay, if the calculated F is greater than the critical value, and I think the critical value will be given to you. You're not figuring that. You're not going to F tables, although you did it in the hypothesis testing, so you never know. Okay, but the examples in this reading seem to give it to us. Okay, we cannot reject that null if the calculated F is less than the critical value. And that would conclude that it's not statistically significant or something along those lines. So, okay, so let's just jump right down here to this ANOVA table. And it allows us to be able to run these calculations to then be able to test our model, the validity of our model. So in this ANOVA table, I want you to be aware that we can read this ANOVA table. We can go down the ANOVA table, and we can also go across this ANOVA table. Okay, so I want you to take this away. So degrees of freedom. Yeah, you don't have to know what degrees of freedom are, okay? But there's a statistical concept that place a limitation on our model. Okay, don't go any further. So, but what you need to know is the degrees of freedom in the regression is just equal to K, and K is the number of independent variables. Well, how many independent variables do we have? Well, we just simply have 1. K is equal to 1. Okay, that's it. K is equal to 1. In the residual, this is also known as the error term, error. Okay, so make sure that you know that, error. So the term residual could also be used. And what are the degrees of freedom here? The degrees of freedom are n, that's the number of observations, minus k, which is the number of independent variables, minus 1. So sometimes you see it written as n minus 2. That would be our case. And in the total model, it's just n minus 1. So if you notice the degrees of freedom in the regression plus the degrees of freedom in the residual or error term equal the total degrees of freedom. So they might give us this table, and you might be able to have to figure out 1 or 2 of the others. Why do we need to do that? Okay, well, could they back us up to calculate the SSR, SSE, and SST? Remember, SSR plus SSE equals the SST. Okay, so that we can figure that out. So we can work down. We've got the formulas. Okay, so remember those formulas over here. I'm putting stars beside them. Just, you know, okay. Listen, if you can't remember these, I don't think it's game over. Remember, okay. I don't think they're going to back you. I really back up to this. I think they're going to give you this table. But what you need to know is, how do you go from SSR to MSR, the mean squared? Well, what we need to do is, as it shows right down here, MSE and MSR, okay, how do we get there? Well, what we do is we divide by the degrees of freedom. So in this case, SSR divided by K is equal to the MSR. There we have it right in this formula. Okay, and here it is, right in this formula right here. Let's just make sure we can still read it. And how do we get the MSE? Okay, well, we're gonna go and divide the SSE. Okay, now I better give myself a little bit of space here, okay, to write this in here. Okay, we're going to divide the SSE by n minus k minus 1, and that's going to equal the MSE. And here it is right here. Okay, why do we need to know this? Because to calculate the F stats, to get this F stat, we need the MSR over the MSE. Okay, so key formulas that you should know. Okay, there it is. Okay, and now one other formula that I didn't break out here, but to calculate the R squared, there it is. It's the SSR over the SST. These formulas are a must. Okay, this, if anything, make sure that you know these, because that's where I believe the questions are coming, and you'll be able to put it together. Okay, now in terms of one other point, I'm going to clear this off. One other point that I want you to take away, because the learning outcome statement actually says use the ANOVA table to calculate the standard error of estimate. Okay, so the standard error of estimate, the SEE, okay, this was the standard error for our model, and we need to use a kind of a sneaky relationship. We've got to back up here to this ANOVA table, and the standard error of estimate is equal to the square root of the MSE. So they may give you this MSE, and you might have to back up to calculate the standard error of the estimate. And remember, this is the error in the model. This is the error in the model. Okay, and what did that mean? The error in the model? Oh, okay, well, let's draw that model again. Okay, and quickly we'll draw this model, and you remember the observations, the actual observations, and here's our line of best fit going right through the middle here, and the standard error of the estimate, the SEE. Remember that looked at the differences from the actual to the predicted, the actual to the predicted, the actual to the predicted. We really want this standard error of the estimate to be quite low. If it's low, then that means that we have a good model. Okay, that's a good model. I'm going to stay away from technical terms. Okay, it means that that the line of best fit, it really does fit the data quite well. Okay, so this is where we're rolling through. And the exercise that I see you coming across here is something like this. So we've got this analyst following the toy industry concluded that the major economic factor influencing the toy industry's U.S. Domestic sales is the number of children, 3 to 14 years old. Okay, so then the analyst gathers 30 observations, and here's the ANOVA table, and here's the regression equation. And they've given us information here. So let's put this together here. So the first thing I want to do is to formulate the regression equation. Okay, so can we do that? Okay, well, we're going to look down here, and remember the regression equation is just going to be, remember, it's going to be y is equal to beta naught plus beta 1 times x, okay, and there's an error term. Okay, we can leave off that error term, but let's grab this information. Where are we getting these betas? Well, they're right here in the table. They're the coefficients. Okay, here's the intercept. Here's the intercept, and this is actually the slope. Okay, the slope. Okay, I've disguised it as saying it's this macroeconomic factor, but it doesn't matter. We can grab these coefficients right there. Okay, and don't worry about whatever the number, just plug it in. So here it is. It is the intercept beta naught. That's 62.1, and then this plus because it's a positive number, and beta 1 is 87.5. 87.5, and x, well, that's just the child, so I'm just going to say whatever c, child. Okay, so there it is. This is my regression equation, and it's really sales, so it's s. Okay, so let's put that in there so we can read it. Sales. Okay, so here's my model, and there it is. I've got my my regression equation. Okay, now in moving forward, it says, let's test for significance of the intercept coefficient. Assume a critical F value of 3.35. Okay, so the question number 2, we've got to back ourselves up here. Okay, we know that this hypothesis is saying, the null hypothesis H naught is saying that the intercept beta naught, the intercept beta naught is equal to 0, and the alternative HA, that beta naught is not equal to 0. Okay, so this is what it's saying. So now we need to test this. We need to calculate the F. So what is the F stat? We need to calculate that. It is the MSR over the MSE. Okay, where are we going to get that? We're going to come up to our ANOVA table here, okay? And we've got to be able to complete this ANOVA table and fill this in. So what do we need to do here? Well, okay, listen, I made this up, okay? So remember, let's start filling this in here. The degrees of freedom in the regression, that was just equal to K, okay? That's just equal to K, and K is equal to 1. That's just the number of independent variables. We have 1. In the residual or in the error term, this is n minus k minus 1. So let's put this in here. So n is 30, k is 1, and take away another 1, so that's going to be 28. And so the total degrees of freedom are n 30 minus 1, which is 29. So that's good because 28 plus 1 is 29. It works out so far. Okay, so now let's work through this and do our calculation. So the SSR divided by the degrees of freedom, that's going to give us the MSR, which is 236.3. All right, the MSE, oh, we've got to get the SSE. We don't even have it. So where are we going to get this? Okay, I just wanted to back you up here. We've got this SST, we've got the total variation, and we've got the variation in the regression. So we can calculate this just by doing some subtraction. So let's just write this over here. Okay, so we're going to write it on the side so we can see this here. So the SSE is going to be equal to the SST minus the SSR. Okay, so if we put in those numbers, so we have 588.71 minus 236.3. And if we do this math, we end up with 588.71 minus 236.3. We end up with 352. We end up with 352.4. Okay, so let's just clean this up and we'll write that in here in terms of our SSE. That is 300. So it's going to be a value of 352.41. Okay, there it is, 41. Okay, that says 41. Let's write that so we can read it here. 0.41. Okay, so with this long-winded approach, how do we calculate the MSE? The MSE is going to be equal to the SEE, which is 352.41. And we're going to divide this by the degrees of freedom, which is 28. Okay, so if we divide this by 28, we end up with a figure of 12.58. Okay, so 12.58. 12.58. Okay, so let's just make sure that we've got that. 588.71 minus 236.3. That gives us 352.41. If we divide this by the 28 degrees of freedom, okay, we end up with 12.58. Okay, and now we can calculate our F stat. So if we come over and we write these values in, the F stat is the MSR, which is 236.3 divided by 12.58. And we end up with a value of 236.3 divided by 12.58. We end up with 18.7. So there it is, 18.7. We can just fit it in there. Here's our F value, 18.7. So given an F value of 18.7 and a critical value, okay, right here of 3.35, we can certainly reject the null. Okay, so we're going to reject this null, and we're going to conclude that the intercept is statistically significant. Okay, so that's how we would run through this. Okay, it said calculate the standard error of estimate in number 3. So do not confuse the standard error of estimate with the SEE. Okay, remember that is not the case. Okay, so let's give ourselves some space over here. Okay, do not confuse the standard error of estimate with the sum of the squared of the error term. Okay, that is a common mistake. We don't want to do that. Okay, so let's see here. The standard error of the estimate, SEE, is equal to, remember, that square root of the MSE. So the MSE was 12.58. 12.58. And so the square root of 12.58. So let's calculate the square root of 12.58. Okay, and we should be able to come up with our value. Okay, so let's do that quickly on our calculator. And so square root of 12.58, and that comes to 3.54. 3.54. Okay, there it is. So the standard error of estimate is 3.54. Okay, let's clean this up a little bit here and shift the the page upwards here, and now we can tackle the next couple questions. Calculate the predicted value, okay, and then so calculating a predicted value. Okay, well, let's just come right back over here. We'll come back to our model, and this is pretty straightforward. All we're going to do is plug in the value for the child, okay, and let's drop that in here. And so dropping this in here, the value for child is just 10. So I'm just going to drop in a value of 10. Let's just get rid of this and put in 10. And if we do this math, then we end up with a predicted value of 937.1. Okay, there it is. That's our predicted value. Now, question 5 says based on your answer to question 4, calculate the 95% prediction interval. Assume a critical value of 2.052 and a standard error of the forecast of 4.23. Okay, and we'll talk about this, okay? But I really think, I really believe that this is going to be given. Come on, they've got to give you that. Anyway, how would we calculate this, this confidence interval? That's really what we're after. And so this confidence interval then is going to be calculated as, so it's going to be calculated as the predicted value plus or minus the t-value, which will be given, the t-value, times this standard error of the forecast. Okay, that's going to be given. Otherwise, okay, I'll show you how to calculate it. But again, I really doubt that that's going back this far. So the upper limit here. So we're going to calculate from this an upper and a lower limit. And so to be able to calculate that upper limit, so I'll just say UL, the upper limit. So it's going to be our value of the prediction, which was 937.1 plus, and here's the t-value. So plus the t-value, which is 2.052, 2.05. Oh, no, why would I write a 3 there? 2.0. Let's get that so we can read it here. 2.053 times the standard error of the forecast, 4.23. And if we do this math, we get the upper limit being equal to 945.78. And if we do the lower limit, then it's just 937.1 minus that t-value, 2.058. Don't just use 1.96 unless they give that, they don't give you a value. You can use that value of 1.96 times 4.23. And if you don't remember where that 1.96 comes from, go back to the hypothesis testing material and you will remember it from there. You'll see it there. You get 928.42. So we've got our confidence interval running from 928.42 all the way to 945.78. Okay, and the last item here is calculating this coefficient of determination. So we've got to go back up to our ANOVA table, and we've got to grab that information. So let's just write it up here on the side here. And so this coefficient of determination, the R squared, it is just simply the SSR over the SST. So this is going to be 236.3 divided by 588.71. So this is going to give us an R squared of 0.401 or 0.4. Okay, and we're going to interpret that information. Remember, the R squared, it's a measure of how well the model fits the data. And so in this case, 40.1% of the variation in the dependent variable is explained by the variation in the independent variable. I think that's really critical that you know that language. And I think you've got to be able to handle these questions. So I think this is good for the first part of the lesson here. So I think we'll cut it off here, and then we will join back up in the next lesson.